Imagine writing code, not on a glowing screen, but by punching holes in stiff cards, knowing a single typo means waiting all night to discover your mistake. In the 1970s, every program was a gamble of patience and precision, and luck. Dropping your deck could erase days of work. Why did anyone keep coming back to those clattering keypunch rooms? The answer reveals just how different and how demanding coding truly was. A single punch card held just one line of code, 80 columns across, rigid as a ruler. For most languages, only columns 1 through 72 counted as source, and the last 8, columns 73 to 80, were reserved for sequence numbers. Those digits were a lifeline. Lose your grip and scatter 1,000 cards across the floor, and those numbers were the only way to put the program back together, one painstaking card at a time. Precision wasn't just encouraged, it was mandatory. The programmer, often a university scientist hunched over a desk, started with a coding sheet, a grid of boxes mapping each column, handwritten in pencil. Every character had to land in the right box. Fortran, for example, demanded statement labels in columns 1 to 5, a continuation mark in column 6, and code in columns 7 onward. One stray mark, one off-by-one slip, and the compiler would choke, sometimes days later, after hours of waiting. Key punch machines like IBM 029 turned these sheets into cards. Each keystroke punched a pattern of holes, the clack echoing through the room. Some programmers punched their own cards, but many handed coding sheets to operators, often women with nimble fingers and an eye for errors. Verification meant running the deck through a second pass, watching for mismatches. A typo wasn't just a nuisance, it could mean a wasted night or a program that never ran at all. Paper tape was another option, especially in smaller labs, but it was even less forgiving. A torn tape or a jam could erase hours. So most stuck with cards, rubber-banded into decks, each one a small monument to patience and precision. Once the last card was punched and checked, the ritual of submission began. Programmers lined up at the operator's window, clutching rubber-banded decks and a slip of paper, sometimes a job control language card on top, sometimes just a handwritten note. The operator, seated behind glass, acted as both gatekeeper and judge. Decks slid through the slot and vanished into trays marked for priority, routine, or overnight. The wait began. Batch queues ruled the mainframe's schedule. Dozens of jobs piled up, each a stack of cards waiting for its turn in the reader. If you submitted at 5 p.m., your best hope was to find a green bar printout waiting the next morning. Sometimes it took longer. The machine was shared by everyone, students, payroll clerks, weather modelers, each with their own deadlines and disasters. When the printout finally appeared, it was a thick, fan-folded stack striped in green and white. The first page might be a verdict, a single cryptic error message, or worse, a hexadecimal memory dump that sprawled for yards. Debugging meant scanning columns of numbers and tracing line numbers back to the offending card. A missing continuation mark in column 6 of a Fortran deck could halt the whole process, sending you back to the keypunch room to fix a single line, then start the waiting game all over again. The operator's word was law. A friendly one might nudge your job up the queue. A stickler could leave you pacing the linoleum for hours. Every programmer learned to respect the power behind the glass and to dread the moment when a simple typo cost an entire night. Every programming language in the 1970s had its own territory. Fortran was the workhorse of science. So if you needed to model the weather, simulate a rocket launch, or crunch numbers for engineering, Fortran was your tool. Its blocky uppercase statements filled card after card, powering physics labs and climate research across the world. COBOL, in contrast, was the language of business. Payroll, banking, and inventory management all ran on sprawling COBOL programs with syntax that was verbose but readable, designed for clarity in a world where mistakes could mean missing paychecks or lost accounts. For those who worked closest to the machine, assembly language was the ultimate test. Every instruction mapped directly to hardware: load, store, branch, repeat. With memory measured in kilobytes and every cycle precious, assembly programmers squeezed efficiency from every line, writing code that ran operating systems, controlled hardware, and made the most of expensive mainframes. BASIC began to appear in university labs, especially on mini-computers. It was approachable, simple to learn, and became the first taste of programming for many students, an invitation to experiment. Pascal came next, introduced in 1970 by Niklas Wirth, offering structured programming concepts that trained a new generation to think in terms of procedures and data structures. Each language had its own strengths, shaped by the problems it was meant to solve and the machines it ran on. The choice of language was not just about preference, it was dictated by the job at hand, the limitations of the hardware, and the expectations of the era. The machines that powered programming in the 1970s were giants. IBM System 360 mainframes filled entire rooms with memory measured in kilobytes. 64 kilobytes was considered generous, a number that today fits in the tiniest corner of a smartwatch. Every byte was precious, and every program had to compete for a slice of that limited space. Magnetic tape reels spun in glass-walled, climate-controlled chambers, and the hum of cooling fans filled the air. Dozens of users shared a single mainframe, their jobs stacked in queues, each hoping for a turn at the processor. Access was tightly rationed, and the person who controlled it all was the operator. Behind the glass, the operator managed the schedule, loaded tapes, and decided whose deck ran next. Programmers learned quickly that a friendly word or a well-timed coffee could nudge a job up the queue. Operators were more than gatekeepers. They were mentors, troubleshooters, and sometimes the only lifeline when a job failed 3 in the morning. Status in the computer center flowed from these relationships. A seasoned operator could save a new programmer hours of frustration or quietly teach the tricks of the system. Community grew out of these constraints. Programmers gathered in waiting rooms, swapping stories and strategies while watching the clock. User groups formed, sometimes informally in the hallways, sometimes as official meetups. Byte magazine, launched in 1975, became a touchstone for sharing discoveries, tips, and the occasional war story. Learning happened face-to-face. Manuals opened between elbows, green bar printouts spread across tables. In a world where mistakes cost days, mentorship wasn't just helpful, it was survival. In 1975, a blue metal box called the Altair 8800 landed on the cover of Popular Electronics for $439. It did not look like much, just rows of switches and blinking lights, but it was a spark. For the first time, a programmer could actually buy a computer and take it home. No mainframe, no operator's window, just a soldering iron, a pile of circuit boards, and a thick manual. The Altair arrived as a kit, with only 256 bytes of memory, enough for a handful of instructions. Yet it was a revelation. It meant ownership. It meant possibility. Within 2 years, the revolution picked up speed. The Apple II launched in 1977 with 4 kilobytes of RAM for $1,298, ready to run out of the box. That same year, Radio Shack's TRS-80 hit shelves at $599, also with 4 kilobytes of RAM. Basic was built in. You could sit at your kitchen table, type a few lines, and see the results instantly. No more waiting overnight. No more green bar printouts. Home computers were still expensive, but compared to mainframes that cost $10,000, they were within reach for hobbyists, tinkerers, and dreamers. The center of gravity shifted from glass-walled labs to garages and bedrooms, and a new kind of coder was born, one who could experiment, break things, and learn on their own schedule. A new way of working began to take hold as the decade progressed. In 1971, Unix arrived at Bell Labs, portable, modular, and designed to run on different machines. For the first time, operating systems could be shared and improved by programmers across institutions. By 1976, screen-based text editors like VI and Emacs replaced the ritual of punching cards for every change. Now, code could be written and corrected directly on a terminal, one line at a time, with mistakes fixed in seconds instead of days. Collaboration leapt forward too. In 1971, Ray Tomlinson sent the first email across ARPANET using the @ to connect people on different machines. By the end of the decade, VisiCalc appeared on the Apple II, turning the spreadsheet from a paper grid into a living interactive tool. These breakthroughs broke the old cycle of waiting and frustration. Programming became more immediate, more creative, and more connected. The groundwork was laid for everything that would follow. Today, code compiles in seconds, and collaboration happens across continents. But every shortcut and abstraction rests on decades of patient physical labor. The ingenuity forged in constraint built the digital world we inherit. Every line we write now stands on the shoulders of those card decks. Thanks for watching.